Everybody, welcome to this weird new reality that is the virtual meeting, the final MinSouth presentation of the year, and our prestige lecture. So this final talk was supposed to be looking at the place of mining in a climate change world, and the conflicts and conundrums that entails. But this is going to be from a slightly different angle. So I'm delighted to introduce our guest speaker for tonight. So this is Neil Kermode. Neil is Managing Director of EMEC, the European Marine Energy Centre, based in Orkney, which works on development of the technology for wave and tidal power. Neil, I don't know if you want to say a bit more about EMEC before you start, or whether you want to go straight on into it. But if you're ready to roll, then you want to share your screen and carry on. Over to you.
Let's see how we go. So, good evening, everybody. This is rather peculiar doing this sitting in the Home Office, and I usually do this presentation standing up, so that is also peculiar. As Sue said, my name is Neil Kermode. I'm the Managing Director of EMEC, the European Marine Energy Centre, and I want to talk to you tonight about the whole issue of energy, and particularly around with a mining context. So I've organised this in three parts, and it's principally about why are we bothering with all this effort that we're putting into trying to make marine energy work. A second part about marine energy, and particularly the material requirements that are in it, that are involved in it, and also then finally a piece on the wider energy picture. I'm going to see how we go. We're planning to run 3/4 of an hour with 15 minutes of questions. We might get to a point when, if you do want to stand up and get blood back into your backside, then feel free to do so, because it will be quite hard, I think, for you listening to me for 3/4 of an hour without some sort of change in pace. So please, if we do, we may well take a break. So here we go. So the first part, why are we bothering? Well, the principal issue, as far as I'm concerned, is that we have a country which has been entirely based on energy, and probably the principal energy source that was used at the time was coal. And taking the nighttime view of the UK and mapping that against the coal measures in the UK, shows principally how we, frankly, colonised areas on top of coal. The interesting point, there's two interesting points in this picture. One is that that's where we are, up in Orkney, and the second thing is the dots that are out in the North Sea to the east. That's all the oil platforms that are out there. There are as many people, or have been as many people, working out in the North Sea as live on our island group of around about 20,000 people. I've now started to get some feedback. So, okay, I think that's gone again. Okay. So we have a society which is shaped by energy, and the way energy is being used and has been used has changed quite dramatically. When I was doing the preparation for this talk, I looked at a variety of things, including this Sankey diagram, which is based in 2014, which shows the different energies, different materials we use for energy. Top left being coal, then renewables, nuclear import, natural gas, and then the oil side of things at the bottom. And the interesting thing to me is that black smear for coal at the top, going down into electricity generation, has now completely ended. There is no coal-fired generation in Scotland anymore, and renewables became the principal source for energy on several occasions in the last few weeks and months. And in fact, I think this morning or yesterday morning was the first time the UK had been not using coal for electricity generation for 2 months, and that's a first since principally the Industrial Revolution. So we have a very changing energy picture, and lifting some more information from 2018, I couldn't find a comparable Sankey diagram that was useful at the moment, but I think it's interesting to note that we do have a slice here where electricity is 19% of our energy, final energy consumption, but the greeny bits, i.e. the petroleum products at 46% and the natural gas at 31%, mean that we are still effectively mining our fuel. But that is going to change. because we know we have to get to net zero by a variety of dates. Probably 2050 was the date that was talked about. 2045 is what Scotland has announced, and there are a number of communities who are intending to go earlier than that, and Orkney is trying to get to there by 2030. So the way in which we are getting our energy is going to change dramatically. So from a mining point of view, I'm sorry, it's going to be bad news, because we're going to stop mining it, we're going to start harvesting it. But the other point I want to go on to is to show that, in fact, there's a huge amount of activity that's needed to make sure that we have the means to generate this electricity. It's also telling, and there's an issue around climate change, but there's also a simple maths issue in some of this stuff, and that is looking at what we've done with oil lately. I think is quite telling. The top left-hand graph shows oil production in the UK, billion barrels per day, and it shows that our oil consumption has been pretty static, but has tailed off a little bit in the last couple of years. The bottom left-hand corner shows the world consumption of oil, i.e. that is continuing to rise. It wasn't in 2016, and the highlighted figure shows the consumption at 35 billion barrels per year. And on the right-hand side, the proven oil reserves have not increased. They've not increased since 2013, effectively. And the point is, we have an increasing demand and a static supply. So we have to do something about it from a simple reserves point of view. But there's a wider piece that I also wanted to make extremely personal, and that is in terms of the atmosphere, because it's kind of getting stuffy in here. And to make it very personal, this is me at 2 weeks old. I can't hear everybody go, but I'll take that as read. And my grandparents, and Tom, when he was born, was in 1898, and there were around about 295 parts per million CO2 in the atmosphere. When I was born in 1959, it was 316 parts per million. And looking at the NOAA information, only a few weeks ago, we just passed 417 parts per million. So we have added 100 parts per million CO2 to the atmosphere in my lifetime, which basically spans this graph. And that's a terrifying figure, because it's estimated if we get to 450, we're probably looking at 2 degrees climate change. And Oregon State University did work that showed the last time we had a consistent 2 degrees climate, warmer climate, we had 6 meter higher sea levels. So from an atmospheric point of view, we know we need to do something else about our energy, and also we know that the planet is getting increasingly crowded. So there's a huge number of people who are looking to increase their energy consumption and their standards of living. And there is and everybody's heading in the same sort of direction in terms of what's been happening with oil. Now that may be tailing off a little bit, depending on what's going on with COVID, etc. But frankly, the overall trend has been continuously up. And so in my lifetime, the world population has doubled, our oil use per person has trebled, our coal or CO2 equivalent has over trebled, and then the oil price has doubled, quadrupled, halved, and then gone all over the shop. So we have a very, very unstable energy picture. We know it's changing. We don't know how it's going to change exactly. And so part of my job is to try and find a way to put together a new energy system. And this is where marine energy comes in, because marine energy is carbon free. It is out of phase with wind. Wind is basically solar energy, which generates convection currents. And a lot of what we're doing is out of phase with wind. It's more reliable than wind because we can predict it several days out, or indeed a millennia out, because tidal energy is based on the planetary movements, and we know where the moon's going to be on a given moment 1,000 years from today. So we can predict the energy that we can extract from the movement of water, and I'll talk more about that in a minute. And in terms of wave being more reliable than wind, the point is that wind blows across the oceans and the waves tend to turn up a few days later. So we've got predictability about when waves are going to turn up. The scale of the resources in marine energy is huge. It's estimated that we could do around 25% of the UK's present electricity demand from wave and tide around our coasts, let alone what can be done elsewhere on planets Earth/water. And there's also no evidence of negative consequences from harvesting energy. So these mean that these are energy sources which are relatively benign. Now, of course, we're removing energy from a system and causing change, but those changes don't seem to be significant. And we've been looking for 15 years or so since we've been working on this, and we're not seeing negative impacts. And the point is, from the UK, this does give us the potential for a birth of a new industry, but indeed for all around the world, there are communities on islands or facing the water who have now or are now waking up to the fact they have an energy source on their doorstep. So in terms of the UK resource, it's quite telling to show where the energy is. And these are two maps that were produced by the Department of Environment, I think it was, back in 1999. I lose track of what the department names were back then, but it shows that it shows the UK territorial waters, and the odd shape is really driven by the fact that Ireland's territorial waters encroach, that was colonial, impinge upon UK territorial waters, and similarly Iceland's do from the top and France does from the bottom. So we end up with this slightly odd shape. But these figures show where the energy is, and you can see that there are some brighter purple colours in a variety of places around the UK, which show the high tidal energy, and the wave energy is shown in some redder colours. And for some indication of energy density, the wave climate here in Orkney, which is just at the top of Scotland, is around about 35 kilowatts per linear metre of wave. That's the average through the year. So there's a significant amount of energy that's incident, and that energy, say, could supply 20% of our electricity, and also gives us an opportunity to build a new industry with a secure supply of energy, which then also reduces our carbon emissions. So this is why we are targeting it for the UK, because we have a particular need. But on a global market, the tidal resource is also enormous. It shows the colours there show where the tidal resource is strongest, and the wave resource is similarly distributed. The wave resource is interesting. It's very strong in the southern oceans because effectively waves run uninterrupted in around the southern ocean, whereas the waves in the northern hemisphere are interrupted by the continents. But waves generally move from from west to east, driven by the spin of the Earth, and so countries with west-facing coasts in those areas have got the strongest wave resources. Overall, the International Energy Agency estimated that there's in the order of nearly 350 gigawatts of energy could be harvested by 2050, and that could be worth around 4 billion to the UK in gross domestic product as an export market. So, and that's not all of that. That's our share could be 4 billion. So it's worth doing it on the basis of energy. It's worth doing it on the basis of there being a market. So the fact that this was a possibility gave rise to the creation of EMEC, and as Sue says, I'm the managing director, and we're the world's first and only accredited grid-connected laboratory for testing wave and tidal energy machines. And I'll give you some indication of scale, because we are not hunched over a laboratory in white coats. This is quite industrial, the work we're doing. And what we've got is an independent facility, so we receive government support to be set up, but we are a separate company, and we have got what we call plug and play infrastructure, which allows people to come and plug in their machines onto our infrastructure. They can concentrate on making their machines work. We will worry about the dull back office stuff. And we've got hard infrastructure and support services in forms of soft infrastructure. And the diagram on the right-hand side shows some of the kit that we have in terms of measuring the weather, what's happening with shipping in terms of marine radar, wildlife observations, telemetry, grid connection, the whole 9 yards. We've got two principal sites. The top one is the tidal site at the place called the Fall of Warness, and the bottom one is a place called Billy Crew, which is our wave energy site. And the wave energy site, not unreasonably, is on the west coast of Orkney, and the next thing out to sea from where we are is Canada. So waves can come in uninterrupted across and pound into that coast that's on the bottom right-hand corner. We get waves up to 17 meters high pounding in onto that coast. In terms of the channel that's there, you can see in the middle, in the sort of the upper large photograph. That body of water between the little island and the larger island in the background is called the Fall of Warness, and that's where our test centre is. We get water speeds going through there at up to about 4 meters a second, so that's 8 knots, and 500 million tons of seawater an hour go through that gap. So we are playing with large and elemental forces here, which are really quite scary, and we need the right materials and the right techniques to be able to manage working in those environments. Test Centre itself, set up with public funding, as I said. We're a not-for-profit organisation, we're a testing laboratory, and we have a vision of getting a globally successful marine energy industry to play its part in the clean energy system. And our mission is to help do that as fast and as cheaply and with as low a risk as possible. And we're working across the areas that are shown in the bottom of the slide. But I said I wanted to give you some indication of scale, and I wanted to do that to make it real, because these are significant endeavours. These are big projects we're playing with. This is an extract of a Google chart showing with the cables that run out into this fast running piece of tide, which obviously runs from sort of top left to bottom right and then reverses and goes back the other way. And now those cables themselves are capable of landing about 5 megawatts of power ashore. These are the cables whilst they were being loaded into the cable ship in Norway, and those cables were then brought over by ship. The cables are spooled off the front of the vessel, floated ashore, and then those buoys are cut off and the cables sink to the seabed, and then the ship basically steams out backwards and unrolls the cable over the bow of the stern. And of course, on any cable you need a connector on the end of it. So this is a photograph of one of our cable ends being lowered over the side of the ship. So yeah, this is big stuff. This is not playing around in the bathtub. This is proper industrial engineering, requiring industrial processes and industrial safety systems to make it all work. Excuse me a second. So the technology itself, and how does it actually work? I've a couple of diagrams just showing the variety of different ways in which these machines work. And wave energy machines principally work with the potential energy that's in the sea. So it's either the fact the sea piles up into a wave and something climbs over the top of it and extends a mooring or stretches something or swills backwards and forwards, whereas tidal energy is principally taking kinetic energy out. So these are effectively a variation of underwater windmill, and these machines interact in the same way with the fluids as wind turbines do. There are a variety of different ways in which this is all working, and at the moment we don't know the best way of doing any of this. We're getting some patterns out of it, so we're seeing a lot of machines which are now floating. We're seeing a lot of machines which have got multiple blades that point into the tide, and at the moment this is a wide open space, and so there's a lot of work to be done to work out what are the right machines to be built. That is particularly relevant because at the moment it is not worthwhile building the production lines to systemize the production of these machines until we know what it is we need to build. So there are intentions and suggestions about bringing in esoteric materials, but at the moment most of these are built with steel. There's some carbon fibre in there. There'll be copper wiring, but as yet we've not got to materials such as pultrusion or concrete structures or things like that. So at the moment it's still in experimental. We might need to change the shape space. So why are we doing this in Orkney? Well, we got a really big, strong waves, as I mentioned, but we've also got close access to sheltered waters. Scapa Flow, which is the body of water in the middle of the Orkney archipelago, is unusual, if not unique, in that it has got a large area of comparatively safe water where both experiments can be undertaken, but more usefully, a fleet can be assembled to then go out into the hard waters to then go and do the installation work. We are the most northerly point on the national grid, and we do have a lot of expertise in the energy environment. We have the Flotter oil terminal here, which has handled 10% of the UK's North Sea oil since it was created. We've got marine contractors, we've got environmental experience, we've got people used to working with a variety of energy systems. So it's a place where there's a lot of this stuff that's there, and that has enabled us as an organisation to help 32 different devices be put into the water from 20 different developers from 11 countries. And overall, we've shown around about £300 million contribution gross value added to the UK economy. The developers, as I say, have come from 11 different countries, and it's interesting to show how this has happened over time. So this graph shows each horizontal line is a different developer, effectively. Each of the vertical lines is a different year. And you can see there was a build-up from our opening in 2004 through to about 2014 when several things happened. One, there was a loss of confidence in wave energy, which felled a couple of the wave machines companies. Secondly, there were some developers, such as the one in the middle, Andritz Hydro Hammerfest, who this company here, who actually then have gone on to sell machines into a commercial plant being run by Atlantis, which is another company who have other machines that are in as well. And then we've also seen some developers choose to exit the market because they didn't feel it was quite right for them. And since then, we've then had a variety of different people coming along at different times with different technologies. And you can see to the right-hand side with 2020, we've got work going on with a number of different developers. I'm going to talk more about those in a moment. But there's been quite it is quite a war of attrition with this process because the sea is unrelenting, and these are big jobs. These take many millions of pounds to get these installations into the water, and unfortunately there's a limit to what you can do at small scale. So at some point you have to commit and go big, and that's an expensive place. And so it has been a challenge to get these machines in, but I have to say we are seeing some real successes, and I'll talk more about those in a couple of minutes. One of the machines that's in the water at the moment, they've just taken it off our site, and it's going to be seeing some refurbishment work done. It's an organisation called Magallanes, who are a Spanish company based out of Vigo in Spain. And the top left-hand corner is a little model. Effectively, they brought on a boat trailer that was installed that they upon which they did some initial testing. And that was then followed by the fabrication of their full-scale machine. And this is a picture of it being installed on our test site. You notice the yellow buoys in the corners as it was being put into position. And the bottom right-hand corner is a schematic, a cutaway of the device. It's a 2 megawatt machine that was connected to the grid in March. I think the following photographs give some indication of the scale of this machine, and the blades are not on this, but you can note the red structure at the bottom is the nacelle, and the blades obviously fit onto this and go up to a distance to under the hull. There are 2 sets of blades there. Sorry, I've gone on 2 slides. Second company I want to talk about is a company called Orbital Marine Power, which is a company started in Orkney, and the top left-hand corner, same sort of model. Same sort of approach. It had a small device installed locally in a sound. It then built the next machine on the right-hand side, the SR250, which is a 250 kilowatt machine. That had about 4,000 hours of operation, which then led to the SR2000, which is the machine, the bottom right-hand corner, which it's been the most successful machine we've had on site to date. And in 2018, that was generating consistently week in, week out as they work their way through a series of trials, and that delivered around 7% of Orkney's electricity week in, week out. Now that's the equivalent of effectively running these islands a day a fortnight on tides. So that's a huge step forward from an idea in a bathtub to getting something that actually is providing industrial quantities of power. And the success of that has then led them to be able to raise the money for the machine which is being built at the moment. And I'll show you some photographs of that later on, with the Orbital O2 machine. They've renamed themselves from Scott Renewables to Orbital Marine Power. And so this is a machine we're looking forward to welcoming in late 2020, which once again will be around about I think it's a 2 megawatt machine, might be 2.1, I can't remember, 2 megawatt machine, and is effectively it's a production or pre-production model for machines which can then be installed more routinely. But this is based on experience, and I'll talk more about that in a second. And then we've got 2 more. One, there's a wave machine called Wello Oy. It's a Finnish company. They had their first machine up here, which they deployed, then came and reinstalled in 2017, and it was then on site for a couple of years, and it survived over 2 years on test continuously, and has then been and survived 17 and 18 meter high waves. And the second machine arrived in Orkney in July. At the moment, their plans are fluid, and we're looking forward to seeing it deployed, and we hope that can be deployed in Orkney. And then the final wave machine is CorPower, which is a Swedish company who have got a different type of machine. Now, interestingly, this one is actually made out of composites. So that is a GRP buoy with a variety of structures around it. But that's another interesting project development. And one of the things we noticed is that when you're doing this work, one idea leads to another, and this our site did lead to an interesting phone call we had with Microsoft, and they came and have deployed their project Natick, which was put in by the Naval Group, a French company, and they have deployed a subsea data center, which is in, you can clearly see in the picture on the bottom right hand corner, which is underwater at the moment, and that's been a test, which I can happily talk about more about energy efficiency later. But that was interesting that we started off working on marine energy and ended up hosting a site for one of the largest companies in the world. But one of the important things with all this, in the drawing it back to the relevance here, is that this kit needs to be proven, and this journey is not clear. And what we really help people do is go through this real sea learning and innovation, because everybody's got a great idea, but it has to be tested and it has to be exposed to the realities of what's out there. And principally, what those lessons that people go through are learned in the following order. You need to learn whether it's installable. You need to know whether the machine will survive. You need to know whether the machine is reliable and keeps working, and you need to know whether you can maintain it and operate it as part of an energy system. And only when you've got answers to all those questions do you know whether you've got something that's cost effective. And the interesting thing is you have to learn those lessons in that order. You will never know if it is reliable if you don't know how to install it. You will never be able to maintain it if it didn't survive. So these lessons have to be learned in this order, and it takes time to work one's way through this. And sometimes you have to go back and learn the lessons again and again until you get it right, and then you progress. So this is a very hard place to operate. And frankly, we're seeing this come down now to a material science issue. We know where the tides are, we know where the resources are, but can these machines be made to survive the conditions which we don't fully understand yet, because humans have never lived in these conditions and endured these conditions. And here's a couple of examples of some of the stuff we don't know. So top left hand corner, biofouling. That's a camera system that has been colonized by barnacles. So there was a lack of attention to how that was going to be prevented. How can we keep camera systems and monitoring systems operating at depth when you can't get in there to go and clean them with a scrubbing brush? The bottom right hand corner, we often think of the sea as fairly flat, and the seabed we assume is flattish as well. Well, this is a picture, a side scan of a section of the Pentland Firth showing the rock strata there and the variability from boulder fields to rocky ledges. And you can imagine the turbulence that's caused by these different sorts of structures. Bottom left, we have two photographs there. The one on the rightish side is one of our instrument packages being retrieved from the water, which has been covered in seaweed. And obviously the package is supposed to look through water, not look through kelp. And the bottom left-hand corner is a lobster pot which is fouled up around one of our cables. And you'll notice the top of that, there diagonally going across it, there's a cable. The top has got black and yellow stripes. The bottom left hasn't, because the lobster pots have abraded off the outer coatings of our cables. And in the bottom right-hand corner is a plot showing vessel movements on one day on our tidal site. And the point is there will need to be the equivalent of air traffic control for the sea, and that simply doesn't exist in a lot of locations, with the possible exceptions like the Dover Straits, but that's pretty much it. So it's a bit of a wild west frontier out there. And the thing is that all these unknown effects then give rise to material science questions, being corrosion, abrasion, fatigue, and the whole thing that's gone through on land is hundreds of times more expensive to correct at sea. So getting the right materials, getting the right type of stainless steel, making sure that that you only use one type of stainless steel and don't put multiple types of stainless steel together and generate electrolytic effects. All these sorts of details have got to be worked through. So there's a massive materials issue to be worked through. I said I'd give you some photographs of Orbital to make it real as to what's going on. Their machine is principally steel. This is a section through it, and it does contain other materials, and I'll talk more about those in a few minutes. But principally, it's a steel structure. In due course, this could well become a composite structure, or it could well become a concrete structure, because you notice that the vast majority of the device is not actually full of equipment. The blue containers really contain the smart gear, so it's the electronics, and those are containerized so they can be fitted in and fitted out. So there's an element of plug and play with some of this material. And the systems at the moment, they're moored on chain moorings, and those are those two vertical lines. You can see the chains going through them, and those chains will run out in catenaries to large weights on the seabed. And one can imagine in due course that we might move away from large weights on the ends of the cables to possibly even pin piles or other less or finer structures, really. And once again, for scale, I think it's really important we understand that this is really about doing something that generates real quantities of industrial power. And this is a section taken at the fabrication yard, and it's one of what we call one of the hero shots that we absolutely expect will probably be up on the mantelpiece of the people in this photograph one day saying, I was there. And this is a cross section through the machine, and the bracketing structures on the top show where the arms go on the top for the arms that will hold the nacelle structures underwater. But the point is, this is about real jobs and real people doing real work in a real world environment, and this is proper, solid industrial activity. This is the place we're on the edge of now, and I think this is very telling, because this is not just an activity that's happening in the north of Scotland, but this is where Orbital supply chain is coming from for the company as a whole. And this is just one company. So there will be other companies doing a huge amount of work in this space, and we need to find the ways to make this all happen. So that's what's going on as a whole. I said, is it worth it? Well, it does actually fit within the industrial strategy very well. In fact, it's a perfect fit in terms of clean growth, something in which the UK's got a world lead. It happens across the country, as I've just shown, and it will result to inward investment. And on a Scottish level, it fits perfectly with the Scottish Government energy strategy. And it's not just about people in welding masks. There are a lot of other jobs and employment going on making this work. This was an aerial photograph of the pier in Kirkwall a couple of years ago, and this pier was actually extended to enable renewables to happen. And on this particular day, there were 4 separate tidal turbines being worked on, which is why there are something like 250 people in Orkney who are working on marine renewables, who have invested in vessels, and quayside infrastructure is being built around it. This is real work. And all of this stuff needs materials to make it work. So I said I'd talk more about the actual material side of things to bring this round to to what's going on in a practical sense. I hope I've shown why we're doing it and something about what we're doing. But I think it's important to also look at the materials inside these structures. So some work was done, and I'm really looking at what's inside tidal turbines. Now, the point is that at the moment we don't have a definitive design, so I've used a report for the TIPA project, and I'm indebted to Gavin McPherson of Nova Energy in Shetland for giving me sight of this report. And this is a piece of work, we'll be able to put a link up on the site if you're interested, which shows what is actually in the box, and that is what's in the turbine. And there are 2 things to remember. One, there's the turbine you can see at the top with the blades, and then there's a yellow substructure. And interestingly, most of the materials are actually in the substructure. This study looked at a number of different turbines and effectively tried to anonymize and work out some generic aspects about how turbines, what will be in them, and where the costs are going to be. And I think there are some useful pieces here. The structure here shows that the vast majority of the materials is reinforced concrete and steel, and that is principally going to be in the foundations, because structures like the one shown on the left will have ballast on them to hold them down. That may change over time because they may become piled, and some people are looking at piled structures. We've had a couple of piled structures here. But you'll notice that the quantity of finer materials is hugely eclipsed by the steel and the concrete in this case. But of course, it's also interesting to look where those materials are, and the foundation, as I said, is the vast majority, and then we can see where those materials are sitting within the structures as a whole, be in terms of the blades, the generator, the brakes, supports, etc., etc. But it's not just the materials; it's the carbon that's embodied in all of this work, and I think it's becoming increasingly important as we understand the carbon balances in these various machines and how they are fitting together. And it's not just a case of what goes in, but it's a case of what is the impact of that material and why these different materials are used that actually really matters. So what's the embodied material? What is the embodied energy in the material that's being created, i.e. what's the cost of winning it, and indeed what's the cost of material lost. And these two tables at the bottom show that the issue of the amount of energy embedded within the materials is very relevant to decisions that are going to be taken on the whole life costs of the machines. And on the left hand side you can see the recyclability of things, and it strikes me that there are two states here. There's either it's not recyclable at all, like the bottom one, like PVC and XLPE, or it's pretty much all recycled, such as the magnets and the steel, and there's nothing that's really consumed in the way that we would consume energy, say in a conventional power station where you might build it, but it's actually the coal or the gas that you shove in that you consume continuously. So I think we're going to see that these machines are going to need to be optimized, not just for the energy they deliver, but the whole life costs. Interestingly, the project, I'm just looking for the notes here, the project did look at the energy payback, and it showed that it says here, under relative conservative assumptions, the energy payback period for the simulated array of turbines, i.e. a group of turbines, was calculated at about 30 months, whilst the carbon payback was around about 25 months. So I think we're confident if we build the machines, they'll work on an environmental basis for the carbon and the energy invested. But there will and may well be challenges around some of the more esoteric materials that go into them, say in the form of magnets and metals. And there's another part as well. It's not. I mentioned reliability being critically important because it's not just what is in it that matters, but it's how long it matters. And these two graphs, don't worry, you don't need to read the text within them. It's the relative ratios of the green and blue that's important. And the top one is an array of turbines, i.e. a clutch, a farm of turbines, with the gross embodied energy. And the bottom one shows the gross embodied carbon. And principally what it says is the manufacturing is the green bit, and the assembly is the light blue sliver towards the top. The operation is the mid blue, i.e. the bulk of the blue section, and decommissioning is the dark sliver right at the top. So we can see that the manufacturing and the operation are the two areas which have got the highest carbon and embodied energy impacts. And so in terms of the relevance for research, it means that if you can make the machines more durable, you repeat the green, you avoid repeating the green, i.e. you don't have to keep remanufacturing new machines. And if you can make it more reliable, you have to intervene less often, and the blue sections shrinks. But I think those are useful to give some indication that the scale, and these projects were planned over a 25-year life, so if they only last half the time, then these numbers deteriorate rapidly. But the point is we need to make sure, and this is why this journey is so important, that people need to understand whether they've got cost effectiveness. So the final piece of the talk, just the last couple of minutes, was really about the wider energy picture. And that is about something that we need to recalibrate on. Because at the moment, there is a general view that energy equals electricity. And it doesn't. Energy and electricity are not the same. This is an extract from the Scottish Government's energy Was it called Scottish Energy Picture? I think it was 2019. It was published. The next one is due out, I think, next week. But it shows that electricity is about a quarter of Scotland's energy consumption, and half of the energy we use goes in heat, and the other quarter goes in transport. And really, what's gone on in the journeys of late is that we have effectively decarbonised our electricity supply. So our electricity supply now in Scotland is from renewables. Occasionally it uses a bit of imported, but it's principally renewables and nuclear at the moment, but nuclear will be coming offline within the next 5 years or so. So we've decarbonised electricity, but we've started the electrification of vehicles. Nobody can help notice that actually the car companies have at last got around to advertising electric cars on TV, hurrah. But electrification has started, and in Orkney at the moment we've got around about 250 electric vehicles. About 2% of our fleet is electric at the moment, and there are plans afoot at the moment to treble that. But we've made very little start on the electrification or the decarbonisation of heat, and there is some work going on, but there's a huge amount to do, and it's the largest slice of the change that we need to make if we're going to get to net zero. So one of the things that we have come across and we've wandered into, which I thought might be of interest, might be a subject of discussion, is that as an energy test centre for marine renewables as a whole, we've ended up straying into working on turning tidal energy into hydrogen. Now this started with one of the this is a picture of one of the tidal turbines up in our site by a company called Open Hydro, and one of the ferries, and we realized that actually transport is a big user of energy, and so we started to think about things, and our thinking went along the lines of, could we use the fact that the tides are intermittent and variable, i.e. you imagine the shape on the outline of those curves is the way generation happens with the tides. It goes from nearly zero to actually down to zero on some occasions to peaks in a roughly sinusoidal way, and of course it's rectified because of the way the tides come backwards and forwards. And we thought that, well, we've got a limit to how much electricity we can export onto the grid, which is the top of the green. Could we do something clever and store energy from peak tides and then discharge that energy in the gaps and then end up with a resultant output of a continuous stream of energy? That's what we thought. We looked into it. So we thought, could we use tidal turbines to do this? And we started to do some work. But some work was done by Exodus and Element Energy, which showed some really interesting figures about the value of hydrogen if you create it. And it principally shows that if you can create hydrogen, and you could do exactly what's shown in the graph above, in other words, generate it back into electricity and put it into the grid. But if you do that, it's worth about 1/20th as much as it would be if you use that hydrogen to propel vehicles. And if you use it to propel ferries, we see it's worth about £4.60 a kilogram. So we started to look very closely at where there was a possibility, and we realised that actually the ferry in the photograph uses about 16 megawatt hours of diesel. So is there a way in which we could use hydrogen to propel this vehicle or this vessel? And that led us to a series of projects, the main one being a surf and turf project, which the schematic on the right hand side shows how we're taking wind and tidal energy and turning it into hydrogen and then using it in another application. I'm a bit short of time, so I'll skip through this quite quickly, but principally we're taking tidal energy into an electrolyzer. We've connected in the community wind turbine as well. That the hydrogen from that is being stored and is then being conveyed down to mainland Orkney, where it's being put into a fuel cell and it's then being used to power ships when they're tied up alongside. The reason we have to do this really complicated process is we weren't allowed to put the hydrogen on the ships as a fuel, and that was because the mariners weren't trained in handling hydrogen, and they had to be trained in handling hydrogen before they would be allowed out. But there was no training course for handling hydrogen because nobody put hydrogen on ferries. So we've had to create a training rig as part of the fuel cell, which will help the training process. Long and complicated. By all means, see me afterwards. I'll explain it in long detail. So we started working on hydrogen, and it's interesting how this has led us into other places, because although we started to solve a tidal energy need, we've ended up doing a great deal more. And this is a picture of a part of the hydrogen store we can store a ton of hydrogen, and we started working with Tidal Energy. The schematic is of the orbital machine. That's led us to trying to find ways to put hydrogen on ferries, which interestingly led us to a distillery who are interested in using hydrogen as a replacement for their kerosene boilers and propane boilers. And more recently, we are now working with a company on a zero emission plane, which has got a hydrogen fuel cell running an electric engine rather than it being a conventional fossil fuel plane. So this has led us into a bunch of different energy related areas, and it's proving interesting, so that we're seeing that different companies are willing to cluster around people doing innovation, and there's a real lesson here. And the final thing I really want to talk to you about, which I find is fascinating as well, is we're working on a wider energy system project here in Orkney called the Reflex project, which is about connecting up the Orkney grid in a different way and putting storage and smart sensing into the grid system. It's funded by UKRI through the UK government, and it is linking together grid, transport and heat. And this is where we're now bringing in lithium-ion batteries, we're bringing in hydrogen, we're bringing in phase change materials for thermal storage, platinum within the electrolyzers, and a variety of materials which are driving the economy of Orkney now. So in conclusion, energy underpins everything we do here in Orkney. It underpins our society, and materials allow that energy capture to actually happen. Without materials, we'd just be banging rocks together. So we have to recognize that the circularity of the material use process needs to be dramatically improved, because we're going to need a lot more materials to make some of this stuff work, and we can't afford to fritter them away. And we have to use what we have to hand now to build what we know we're going to need for the future. And the final point really is that doing stuff, you find things out. Innovation opens up opportunities, and we've absolutely seen how a number of people have come to see what's happening. When the present situation recovers, if it recovers, and we are able to travel again, please do keep in touch, and please do think about coming to see what's going on. We've got a website which is there, visible in the bottom right-hand corner, but you can't beat coming and seeing the future for yourselves. Please do come along and have a look. I'll finish it at that. Sue, I'll hand back over.